Okay, today's lecture is on free radical copolymerization. At the beginning of this class, we have learned about various types of copolymers, right? And many of those copolymers can be polymerized by free radical polymerization. Okay, and especially the reactivity of specific monomer determine the different kinds of copolymers. So we learn about them. Okay. If you review what we have learned at the beginning of this class, there are different kinds of polymer. For example, there is alternating copolymer. Sorry, I'm gonna write it down again. Alternating copolymer, like AB, something like that. There are random copolymer, basically the random arrangement, AAB, AAA, BBAA, something like that. There's also block copolymer. Okay, basically A, B, A, something like that. Also graft copolymer, so basically A with some branch, right? All right. So how can you make different kinds of copolymers? Okay. To deal with this copolymerization by free radical polymerization, we'll consider only binary case. So basically there are two different kinds of monomer, M1 and M2. Okay. So there are four possible reactions. Radical ending with M1 radical react with M1, forming another M1 radical. Same M1 radical react with monomer M2, so we only consider binary case, forming M2 radical. Similarly, M2 radical react with M1, forming M1 radical. Also, M2 radical react with M2, forming M2 radical. So there are four different possibilities. Okay. For each reaction, we denote the rate constant as K11. So monomer 1, the radical 1, monomer 1. This one is K12, radical 1, monomer 2. This one is similarly 2,1 and K22. Okay. And to solve it, we assume steady state approximation. So basically, the change of radical M1 same as change of M2 radical as a function of time, which is equal to 0. Okay, then K12 M1 radical M2 should be equal to K21 M2 radical M1, right? So if you rearrange it, you have the ratio between two different radical, M1 dot and M2 dot, which is K21 M1 over K12 M2. Okay, this is the first equation. Okay, this is the ratio of the radical concentration. Then let's express the change of monomer M1 as a function of time. So from the original 4 equations, we can express it, which is K11 M1 dot M1 plus K21 M2 dot M1, right? Similarly, dm2 dt is equal to K12 M1 dot M2 plus K22 M2 dot M2. Okay, if you basically divide the first equation with the second one, then you get d m1 over d m2, which is equal to K11 M1 M1 dot K21 M1 M2 dot K12 M2 M1 dot K22 M2 M2 dot, right? Okay, so basically what this means is the ratio of monomer M1 and M2 inside of copolymer, right? Ratio, the basically instantaneous ratio of monomers in copolymer, which have this form. Okay. Okay. If you rearrange it, if you divide numerator and denominator by m2 dot, okay, then you get m1 dot over m2 dot plus k21 m1 over k12 m2 m1 dot over m2 dot plus k22 m1, right? And you can remove this part by using this. Okay, then if you rearrange it, what you get, I'm going to skip the details, K11 over K12 times M1 M2 square plus M1 over M2 over M1 over M2 plus K22 over K21. Okay, right? So we have this expression. So this is the second. This is the second equation. Okay, basically the second one. If you combine the first and the second one, sorry, oh, this is it, and okay, and you define new variables, small r1 and small r2, which is defined as r1 is defined as k1 11 over k12, and r2 is defined as k22 over k21. It's basically the relative ratio of the monomer reactivity, right? Okay, then you can put this in here, and you basically get, if you rearrange it, what you get is, where is it? Okay, this is R2. Okay, so let me just write it again, just R1 m1 m2 square plus m1 m2 m2 plus r2. Okay, if you multiply m2 over m1 in the denominator and numerator, okay, then what you get is 1 plus r1 m1 over m2, 1 plus r2 m2 over m1. Okay, so this equation basically represents the instantaneous ratio of monomers inside of copolymer. It's given in this equation, which is called copolymer equation. Okay. Okay, so let's try to understand what would happen for the structure of copolymers depending on R1 and R2. So R1 and R2 is defined as this. Okay, let's say that R1 is 0, which means that K11 is 0 or K12 is infinite. Okay, so the radical M1 radical does not react with another M1 monomer. Okay, it only reacts with M2 radical, right? M2 monomer, right? And if R2 is also 0, okay, so K22 is 0 or K21 is infinity, which means that M2 radical does not react with M2 monomer. It only reacts with M1, which means that the resulting copolymer will have this kind of structure, M1, M2, M1, M2, something like that. So this condition basically gives us alternating copolymer. Okay. In another case, this first case, if R1 is 1 and R2 is 1, what would happen? So in this case, K11 is equal to K12, K22 is equal to K21. The relative reactivity ratio of monomer 1 and monomer 2 are basically same. Then we would have random copolymer. Right? Okay. Basically, the copolymer composition will be same as the monomer composition. In another case, if R1 is much greater than 1, what would happen? Also R2 is 1. So basically, K11 is much greater than K12, K22 is much greater than K21, which means that it tends to have homopolymer, right? Okay, and somehow if it reacts with another monomer, like radical M1 reacts with M2, then since K22 is much greater than K21, it will also form M2 polymer. So they will basically form black copolymer. Okay, so it all depends on relative value of R1 and R2. Okay. All right. So here we define other variables, small f1 and f2, which is defined as the mole fraction of monomer M1 and M2 in feed. And large F1 and F2 is defined mole fraction of M1 and M2 in copolymer. Okay, so basically the expression copolymer equation that we obtained here this equation dm1 over dm2 relative copolymer composition of each monomer is basically f1 over f2, right? And monomer concentration, the ratio of monomer concentration is actually same as f1 over f2. Okay, so if you combine this definition and the previous two equations, equation number 1 and equation number 2, if you combine them, you can have expressions for f1, which is equal to, I'm going to skip the details, which is equal to r1 f1 squared plus f1 f2 over r1 f1 squared plus 2 f1 f2 plus r2 f2 squared. Okay, you have this equation. Okay, we have this equation. So basically the composition of monomer in copolymer is a function of monomer feed and also reactivity ratio R1 and R2. Okay, so let's see more details about in which case we'll have different kinds of copolymer. So the first case is called ideal copolymerization, copolymer, or random copolymer. Okay, this one holds when R1 times R2 is equal to 1. Okay, so it could be R1 could be both 1, or R1 could be like larger than 1 and R2 could be like smaller than 1, or vice versa. Okay, in this case, the copolymer equation m1 over dm2 becomes, if you rearrange it, you'll have this expression over m1 plus r2 m2. Okay, so if you use this relation, then you'll get, which is r1 times m1 over m2. So basically the composition in copolymer is proportional to the monomer feed composition. Okay, and in this case f1 is equal to, from this equation, simplified r1 f1 over r1 f1 plus f2. Okay, all right, so if you plot the relation between f1 and f1 small f1, both value will be from 0 to 1. Okay, when r1 and r2 are both 1, okay, then you'll have this line. Okay, basically f1 is equal to large f1 is equal to small f1. Okay, the compositions are basically same. Okay, on the other hand, if one of them is larger, if r1 is larger than 1 and r2 is smaller than 1, you have this kind of graph, while when r1 is smaller than 1 and r2 is larger than 1, you have this graph. Okay, so anyhow, if r1 and r2 are equal to 1, you'll have, as I already mentioned before, you have random copolymer. Okay, copolymer composition is basically same as monomer mix composition. Okay, all right. Okay, how about other cases? alternating copolymer. Okay, we have already seen when R1 is equal to 0 or one of them is 0, then we'll have alternating copolymer. Okay. If R1 is equal to, both of them are 0, we have perfect alternation. If it's not, it's alternating, but it's not really perfect. Okay? So basically, you have this kind of graph, f1, small f1. When R1 and R2 are both 0, we have this graph. This is like 0.5. Okay? There's another case. If both R1 and R2 are smaller than 1, the resulting graph, if you draw the graph, will look like this. So we have a isotropic line, and the resulting graph will be something like this. Okay. So basically, the graph, the blue line, cross this point at which f1 is equal to f1. Okay. So this composition, when monomer composition is basically same as the copolymer composition. Okay, that point is called azeotropic point or azeotropic copolymerization in that point. Remember what azeotrope is in from physical chemistry class, right? Okay, that's given here. Okay. All right. Okay. In another case, if either R1 or R2 is equal to infinity, let's say both of them infinity, we will have just homopolymer, because one of the monomer is much more preferred compared to other monomer. Okay. Okay. So let's go back to alternating copolymer case. So in this case, the copolymer equation becomes, since R1 and R2 are 0, so we'll have dm1 over dm2 is equal to m1 over m2. Okay, and from the original, this equation, copolymer equation, the second one, if you do the rearrangement, and since another equation, you will have m1 over m2 is equal to r2 minus 1 or minus 1. So as a result, anyhow, you'll get this relation, f1 is equal to 1 minus r2 over 2 minus r1 minus r2 for alternating copolymer case. Okay. I'm sorry, not alternating copolymer case. When the azeotropic copolymerization case, when f1 is equal to small f1. Okay, when copolymer composition is same as the monomer composition, you'll have this relation. Okay. So when monomer composition f1 is given by this kind of reactivity ratio R1 and R2, then that resulting copolymer has the exactly same composition as small f1. The large f1 is same. Okay. Okay. All right. Maybe we have covered pretty much everything. Some other instances will include when one of the reactivity ratio is equal to 0.5, for example, if R2 is 0.5, okay? Then, if R1 is also 0.5, we'll have azeotropic point here in the middle. But if R1, this is R1 is a 0.5, if R1 is larger than 1, then there will be no azeotropic point. Okay. In another case, if both R1 and R2 are larger than 1, then the resulting graph would look like this. Okay. Basically, it tends to be a black copolymer. Okay. But in reality, it's not really the common case. Okay. All right. So let's wrap it up here. Okay. And all right. Previously, for the free radical copolymerization, we have learned that by checking the reactivity of radical for the different type of monomer R1 and R2, the values of R1 and R2, from the values of R1 and R2, we could predict which copolymer we would get, if it is alternating copolymer or it is random copolymer or block copolymer. Okay, then how can we determine these two R1 and R2 value by experiment? So experimental determination of R1 and R2. Okay. Overall, there are two different methods, but it's pretty much same. The first method is called Mayo and Lewis method, which was proposed and developed by Mayo and Lewis. You might recall the copolymer equation. Okay, if you rearrange it as a function of reactivity efficient R2, for example, R2 can be written as M1 over M2 times dm2 over dm1 1 plus R1 M1 over M2 minus 1. Okay, so M1 and M2 are monomer feed, so we can just control it by experiment. dm2 over dm1 can also be determined. This is just the monomer ratio of inside of the copolymer, which can be determined by experiments such as like NMR. Okay, so we can determine M1 over M2 or dm2 over dm1. Okay, then what you do is you simply plot R2 as a function of R1. But here we don't know what R1 is, so we assume, so with various assumed values of R1, and since we have all the information about these constants, right, you can just plot R2 as a function of R1. They should be proportional to each other, right? Because the other parts are all just constants, right? Oh, sorry. So we'll have some linear plot, okay? And you do the experiment with different monomer feed, for example, okay? Then we also plot R2 as a function of R1 with assumed various values. Then you have another linear plot. And if you have at least 3 plots with different M1 and M2, okay, from the intersect here, it will be not exact intersect. It will be some triangle. Okay, so if you enlarge it, you have like this kind of triangle. So the middle point, right, from here will be the R1 and R2 value, which were experimentally determined. Okay, there could be some experimental error, right? But if this deviation is small, then we can calculate, we can determine or measure R1 and R2 more with more accuracy. Okay, this is one method. The other method is also pretty much same. The second method is called Feynman and Roth method. Feynman. Okay. If you recall, large F1 was R1 F1 square F1 F2 over R1 F1 square plus 2 F1 F2 plus R2 F2 square. Okay, if you rearrange it, what you get is F1 times 1 minus 2 F1 over F1 1 minus F1 is equal to R2 plus F1 square F1 minus 1 over F1 times 1 minus F1 square R1. So we have R2 here and R1 here. Okay, and the other parts, these are pretty much these are all constants, right? F1 F2 or large F1 F2, you can just determine it, right? These are basically constant. Okay, so we can change the monomer concentration, also determine the experimentally copolymer composition. Then these two constants can be determined, right? Then we can plot A as a function of B with different values. Okay, that will be linear, right? And from the slope, okay, we'll have R1, and from the y-intersect, we'll have R2, right? All right. So these two experimental methods to determine R1 and R2 are just the textbook method. Okay, just to explain how to determine it experimentally. But already many people over the last few decades have determined these R1 and R2 values for various kinds of polymerization systems. So you can find those values for different pair of monomer and radical, etc. Okay, you can find it in the tables of the textbook. Okay. All right. So from now on, let's learn more about what factors affecting free radical copolymerization. Affecting free radical copolymerization. Okay, so I just skip the writing. There are many factors. For example, reaction medium or the solvent can affect free radical polymerization. So for example, like the solubility of monomer, pH of the solution, viscosity, etc. Okay. Secondly, polymerization temperature also affect the degree of free radical copolymerization. So for example, since R1 is defined as K11 over K12, since K is a rate constant, we can express it as Arrhenius type equation. sorry, this is 1 1 minus 1 2 over RT. Okay. All right. Thirdly, pressure can also affect the copolymerization. So we although we have not learned about it, the pressure dependence of R1 is given in this equation. V is volume of RT. But these two, temperature or pressure, has very small effect only. The effect is very small, little effect. Okay. On the other hand, the fourth and the most important is the chemical structure and reactivity of monomer and radical, which affect significantly on free radical copolymerization. Okay? All right. Overall, there are three different factors, the small factors in this structure and reactivity, which include resonance stabilization. We know what resonance stabilization is. Resonance stabilization of monomer and radical. Polar effect, basically the polarity of the monomer, and steric effect. These are three major factors in terms of chemical structure and reactivity, which as a result affect the overall free radical copolymerization reaction. Okay. All right. Before we so let's we'll learn about these one by one in more detail. First, resonance stabilization. Before more detailed discussion, let's first define new variables RA and RB, and large capital RA and RB. So small RA and RB is defined as the monomer reactivity ratio in copolymerization, and large capital RA and RB are defined as active center, which is free radical reactivity ratio. So, for example, among two different monomer and radical AB, RA can be written, basically defined as KAA over KAB. Okay. So when you write have written the rate constant K, the first was the radical and the second was the monomer, right? So for A radical, the relative reactivity of A monomer over B is defined as RA. Okay. Similarly, small RB is defined as KBB over KBA. And active center reactivity, the free radical reactivity RA can be defined as KAA over KBA, right? Here, since we have same monomer A and the different radical A and B, the relative ratio, and RB is equal to KBB over KAB. Okay. So these four terms are related to each other. For example, Ra is KAA times KBB times RB. Similarly, RB is equal to KBB over KAA times RA, something like that. Okay, so small r or large r basically represent the relative reactivity of monomer and free radical, okay, in copolymerization. Okay. All right. So let's look at the table 9.1. From the textbook. Okay. From the textbook, if you look at table 9.1, you have relatively large table. There is monomer A and monomer B, and they show our small ra, small rb values, and also their product. So let's just write down a few of them. If monomer A is styrene, so all same styrene. If monomer B is different, like butadiene, methyl methacrylate, methyl acrylate, acrylonitrile, maleic anhydride, and vinyl chloride. Okay, as you see, they all show different Ra and Rb value: 0.78, 0.52, 0.75, 0.40, 0.02, 17. Rb 1.39, 6, 4, 0.02. Okay, with the same monomer, if you react one single monomer, the styrene, with different types of monomer, as you can see, relative reactivity of monomers are quite different, right? For example, if you react styrene with butadiene, Ra, reactivity of styrene compared the monomer styrene compared to butadiene is 0.78. On the other hand, reactivity of butadiene compared to styrene is larger than 1. Okay, so all they have different values. Okay. Why? Let's see why. Okay. If you compare the chemical structure of these different types of monomer, you can understand why. Okay. Basically, the reactivity, and also let's see another table. Let's see. It's not here. Let's see another table from. Okay, so this area basically only shows the monomer reactivity ratio. We also need to check this radical reactivity ratio. For this, we don't have table in our textbook, so let's use the another textbook. So we have this table from Odian book. Okay, if you look at the table 6-3, this is the textbook Odian's Principles of Polymerization. The column, the left column, shows different types of monomer, and this part, the rows, basically shows the different types of radical. Okay, because monomer and radical react with each other to form copolymer, right? Remember? Okay, and they show the relative reactivity as 1 over r, 1 over small r. Okay, Okay, as you see, there are some overall trend. Okay, let's see. For example, let's fix the polymer radical as vinyl acetate. As you see, from here to here, relative reactivity increases. Right? Okay, this shows the general reactivity, order of reactivity from vinyl acetate to 1,3-butadiene. Okay. On the other hand, if you fix the monomer, let's say we fix anything like, for example, styrene. Sorry, butadiene. Fine. So the order is actually different from here. What I mean is the order is different between column and row. This is 1,3-butadiene, styrene, MMA, something like this. But here it's different, right? 1,3-butadiene, styrene, methyl methacrylate here is here, right? And acetonitrile, etc. Okay. But anyhow, the overall, it's not exact, but overall reactivity of the polymer radical is in this direction, right? So because acrylonitrile should be written between methyl vinyl ketone and methyl acrylate, so it should be like here, right? Okay, so overall, so what we can see is that depending on the chemical structure of either monomer or radical, the relative reactivity is different. Okay, we need to know why. Okay, all right. So that is because of resonance polymerization by different types of substituents. Okay. Substituent effect. So if you recall those different reactivity of different substituents, so sorry. Okay, substituents. The reactivity of monomer basically increases as you have substituents which can stabilize the resulting radical by resonance stabilization. Okay, so if you recall, substituents such as phenyl group, vinyl group, cyanide, alkoxy, carboxylic acid, ester. So from in this order, since the substituents on the left side have much greater resonance stabilizing probability, okay, the ability, okay, so with these substituents like styrene, butadiene, okay, the acrylonitrile, etc., they have much greater reactivity compared to other substituents. Okay. 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 So, if I summarize in sentence, substituents that increase monomer reactivity do so because these substituents stabilize and decrease the reactivity of the corresponding radical, right? So if monomer is very reactive with certain substituents, okay, they will be changed to right radical. Okay, if monomer is very reactive, okay, which means that the resulting radical, because the monomer will react with radical, right? The resulting radical should be stabilized by resonance stabilization. Okay, the product, basically the product should be more stable compared to the reactant, right? So by this kind of mechanism, the different substituents affect the different degree of reactivity of monomer and also the radical. We also have different table. Let's see, where is it? I'm sorry. Okay, so 6 point. Actually, we have to see. Oh, sorry. That table. Sorry. Okay, but I don't know how to rotate it. So if you look at those table, that table shows the rate constant for radical monomer reactions. So since we do not have it here in our textbook, we don't really have it. So if you recall, let me just write it. So I'm sorry. 6 point. Not this one. This one. I don't know how to rotate it. Let's rotate this table. Okay. So if you look at this carefully, okay, although it's rotated, okay. If you look at table, the number inside of this table shows basically the rate constant. Okay, and for example, if you fix the monomer like butadiene, okay, the relative rate constant between like styrene and like where is it, like vinyl chloride, it's like huge difference, right? 280 to 319,000, right? So about almost like over 1,000 difference, right? And if you fix the radical now, let's say we just use any radical like vinyl chloride, the difference of the monomer like butadiene and let's say like vinyl acetate, right? It's like 319,000 to 6,000. The difference is like 50 times, right? It's much smaller difference, right? So what this tells us is that if you just saw what you have just saw is the effect of different substituents on radical reactivity and monomer reactivity, which is given as the rate constant, right? How fast the reaction is, okay? And you have just seen that substituents, different chemical structure of substituents, have much larger effect on radical reactivity, okay? But the effect is totally opposite, right? One substituents increase the radical reactivity, while the same substituents decreases the monomer reactivity. Okay, so they are compensated with each other, right? So the overall rate, propagation rate, is not that large. Right? For example, you just saw that for radical reactivity was like 1,000 times. For monomer reactivity, it's like 50 times, right? They are compensated with each other. So overall effect on overall rate of the polymerization is like much smaller, like tens, about like 10, 15 or something like that. Okay, all right. Okay. Another thing to consider, basically same thing. So we can more quantitatively understand the effect of resonance stabilization in terms of the interaction between radical reactivity and monomer reactivity. Okay, that can be done by looking at the reaction energy diagram as a function of reaction coordinate, which is also given in the figure. Okay, something like this. So this figure, if you look at this figure, what this figure shows us is that it shows energy diagram, right? We are familiar with this, right? There are two different kinds of diagram. One of them looks like this, right? Like this. There are four of these lines, these red lines. They basically shows energetics of the approach of a radical to a monomer. Basically, they are reactants. Okay, and these two lines shows the energy of the resulting polymer radical. Okay, two different radical here. Okay. Okay. Right. So they show different values of, for example, like enthalpy change or activation energy, etc. Right. So let's take a look at this figure and just let's go back to the textbook here. Okay. If you recall, the overall energy diagram looked like this. Right. There are four of these kind of lines and like this kind of line, right? Something like that. Okay. Okay. So there are four different kinds of reaction possible between radical and monomer. For example, the radical which is not stabilized by resonance type stabilization react with monomer which is stabilized by resonance with specific kind of substituents, forms radical which is also stabilized by resonance stabilization. The other possibility is something like this. So there are four possibilities. So here the small s denotes the resonance stabilization. Okay. So if you compare for these four different reactions, if you compare the enthalpy change and activation energy, the values are like this. Activation energy. Okay. Since the first reaction has the smallest activation energy which means that first reaction is the most like the fastest reaction compared to other three. Okay. On the other hand, the fourth reaction has the largest activation energy, which means that it's the slowest reaction. Okay. So based on this activation energy or enthalpy, which is thermodynamic data, right, which can tell us the relative reactivity of each reaction among these four reactions. Okay, and those data we already have seen a few of tables, right? The table data and these data quite correspond to each other. Okay. All right. So these were the resonance stabilization case. All right. Another effect. So we covered the, where is it? So first resonance stabilization. Second effect was polar effect. The polarity of each species, radical and monomer, also affect the overall copolymerization. If you look at the another table, which is given here, 6.6. This also, sorry, can really see it. So if you look at the table, let's say that we have some table which shows the different values of R1 times R2 reactivity ratio. Okay. Okay. So the polarity of each species, the polarity of radical and monomer also has huge effect. Okay. And if you compare the R1 and R2 value, and if you multiply it, and if those numbers are much smaller than 1, okay, that has tendency, these two molecules, these two species has tendency to form alternating copolymer. You already have learned about this, right? Okay, so there has been an effort to quantitatively describe this radical monomer reaction in terms of this polarity, and which is called, one of them is called QE scheme by Alfred Price. Okay, what he did is simply, if you have information about R1 and R2, we can predict the polar resonance effect, and we can have guidance to which kind of copolymer we would have. Okay. So, for example, for this kind of copolymerization reaction, right? Okay. What Alfred Price did was that K12, the rate constant, can be written in this form: P1Q2 exponential minus E1 E2. Here, P1 represents the resonance stabilization of M1 radical. So resonance stabilization of M1 radical. Okay, and Q2 represents the resonance stabilization of M2 monomer. Okay, so this is M1 radical. So Q2 represents resonance stabilization of M2 monomer. So basically P and Q represents the relative degree of resonance stabilization of radical and monomer respectively. Okay, and E1, E2 represents the polarity of M1 radical and M2 monomer. Okay. This is it. Very simple, right? Okay. So since we can represent the ray constant in this way, we can write R1 as Q1 over Q2 exponential minus E1 times E1 minus E2, and R2 as Q2 over Q1 exponential minus E2 minus E1. Okay, so if you multiply R1 and R2, what you get is exponential minus E1 minus E2 square. Okay, so since small E1 and E2 represents the polarity of radical and monomer respectively, if there are large difference in polarity, E1 and E2, then R1 times R2 would be decreased, right? Then the copolymer would be more alternating copolymer, right? Okay. All right. So if you look at the general observation in regarding this polar effect, let me just write down the general observation. Okay. Similar Q values, so which is Q and P actually, similar Q, P values and high E values of opposite sign. So Q and E values are already given in tables for different kinds of monomers and radical, gives more alternating copolymer. Similar Q and similar E values gives random copolymer. Finally, large Q difference does not give copolymer. Okay, so anyhow, if you have information about small r1 and r2, the P, Q and small e values, they are already given in the table. Okay, in any textbook you can find it. For example, in our textbook, table 9.2 gives us those information. By simply putting those numbers inside of here, we can easily predict the reactivity ratio and what kind of copolymers we would get. Okay. All right. Finally, third effect was polar effect and static effect. Static effect is when you use different monomer. For example, let's write down one table here. It's also ray constant for different radical monomer combination. So we have like radical here, it's a monomer. So we have vinyl chloride chloride, vinylidene chloride, vinylidene chloride, and trichloroethylene, trans 1,2 dichloroethylene, cis 1,2 dichloroethylene, and yeah, just right there. Finally, tetrachloroethylene. And let's say we have radical is like vinyl acetate, polymer radical. And if you compare the rate constant, we have 10,000, 23,000, 3,480, trans is 220, 65, 338. All different monomers shows different reactivity. Okay, if you look at the chemical structure, so vinyl chloride looks like this, HCl, vinylidene chloride, Cl, H, right? Trichloroethylene, H, trans and cis, Cl, H, Cl, H. Okay, pretty much same, but different number of substituents and different position of substituents. What you can see first is that if you compare vinylidene chloride and either cis or trans chloride, both of them have 2 hydrogen and 2 chlorine atoms, right? And this molecule as 1,1 substitution has much larger reactivity compared to 1,2, 1, so carbon number is 1,2, right? 1,2 substitution. The reason why is that if there are chlorine atoms attached to the second carbon number 2, there will be much more steric hindrance between this monomer and attacking radical. Okay, there will be the radical. Okay, because of these large chlorine atoms. Okay, and if you compare trans and cis, okay, trans is a little bit more stabilized compared to cis, as you all know, and also this cis isomer is not completely coplanar in transition state. Okay, that results in relatively bad, actually really bad resonance stabilization of radical. So the reactivity is very small compared to trans. Okay, so all these effects are based on steric effect, right? The chemical structure. Okay. So there were